Okay, so welcome back. So this video basically is the second part, and what we did was watch this video, Professor David Blai's probabilistic topic modeling and user behavior, for the first 28 minutes when he covers the basic idea of LDA in a big hurry, and then we covered from 49 minutes to 53 minutes a little bit about philosophy of probabilistic modeling, and so I highly recommend that. This is the paper you're supposed to have read, and so now let's jump in here. So I have sort of two main data sets, and I was trying to make the second one like more like exercise, like you wanted. But I know I haven't gone and deleted some sets, but some of it won't work, it'll break, and you can try to fix it. So this one's something I did, Cornell Movie Dialogues, where I was doing this as an open source business use case for my little company with one other guy. So we were basically consulting for a big company in Australasia that does telemarketing stuff. So they record the telephone conversations of other companies to help their managers better understand sort of whatever business relationships. So they do like very standard searches and things like that. So you can search, did anyone say some word during this period, that type of clustering. What they wanted to do was some kind of machine learning. So I simply took out of the box LDA with very minimal changes to do a proof of concept for them. So their data scientists can quickly take this prototype and adapt it to their telephone conversation database, which essentially was audio records that could go through Google's API for deep learning based transcriptions, and then those transcripts will be fed into this LDA cycle. So you get sort of topic modeling. So the managers can kind of go in and say, okay, here are the guys that are really good at customer relations, like what is common to them, and maybe learn some whatever they want. Okay, so that's why I did this. And for this reason, I needed this particular data set because Cornell Movie Dialogues data set is a really neat data set where it has dialogues in lots and lots of movies. And so dialogue is, a couple people talking to each other in a scene in a movie. So it kind of mimics a quick telephone conversation, and that's why I used it. Okay. But now I think the loading, so let's go to, so let's go back to this guy. So this is a standard data set, the 20 news group one. And if you want to load this in the community edition, all the steps are down here. So, how to download the data set and load it in DBFS. So this is, but I believe I should have done this. So let's just find out. I believe there must be, oh yeah, right. So is this already there? This is actually, should be already in the community edition. Databricks datasets, news20.binary, and they have like broken into test and training. So because this is like a standard dataset for topic modeling, news groups dataset. So it's already here.
I don't have a step one. Yeah. Step 0 and step 2.
Oh, really?
Yeah.
Okay, what do you mean step?
You did it.
You have step 0 and then step 2. Step 1 is missing.
Oh. Okay, so maybe, okay, so there is, so this is the way to do it. So if you want to download it from scratch, okay, but I don't know if this is a good idea to do it now, but if you can download the whole thing and then, follow these steps. And unfortunately, it'll take 10 minutes to run. So if you want to do that now, you can just load the data, you have to copy this, and then you will have your sort of data set in this format. You can put it in your own datasets folder. Okay, so this is what maybe you should start this process while we're sort of looking at the code. Okay. So, okay, there's a lot going on with understanding, what's really in LDA formally, but but at a high level, it's not that complicated, right? So the main idea is you want to have in your sort of mind here is these little pictures I've drawn on the blackboard. So what you're trying to do is, so this is a 3-simplex, right? So each axis is the probability of each word. So I'm taking just 3 words, this baby example, and 2 topics. Okay, K is 2, V is 3. Should I turn on the light? Yes. Okay, so maybe I should also turn this way. Sure. Oh well. Okay, so so basically, so we have probability of word 1, probability of word 2, and probability of word 3 in this axis. K is generally less than the number of words because you're trying to find fewer topics to understand lots of words. So the way you represent an observed document is like this, one of these open circles. It's a point in the 3-simplex. So this is sort of the triangle subscript 3. It's points that sum to 1, probability. And so you basically take each observed document and put it there by simply looking at the frequency of each word in that document, right? That's the 3mer. So these are different documents. Of course, the number of words will be 10,000 or something, so it's very high dimensional simplex. And then so then you have to come up with a topic, right? So it's a generative model, so it'll generate a topic somehow. So suppose you have 2 topics. So at the end of this optimization, you find 2 topics. Then the generated document, the way the forward model works, will generate this particular point, right? So it's a generated document, and the point is this generated document is somewhere between these 2 black points, right? That's why it's called, I don't know what statisticians call this, it's a mixture, it's not just a mixture model, it's admixture mixture model. So it's, that's what David was saying, right? So so what so what this means is you can have lots and lots of documents, and then you find K topics, you fix K ahead of time, and then when the model is optimizing the likelihood function for this generative model, what it's basically trying to do is to find topics whose low dimensional simplices are very closely approximating the observed document. So these are essentially, there's a projection from the 3-simplex to the 2-simplex. So this is the other way to think about it, slightly abstractly, is it's a dimensionality reduction method. What it is trying to do is each document is a point in the 3-simplex. Each topic is a point in the 3-simplex as well. And then each generated document is a projection from the 3-simplex to the 2-simplex, from simplex with the vocabulary size to the simplex with the topic size, right? That's at least some super high level. And in the generative model, the plate diagrams, what's being done is, you have a word, it's assigned a topic from so one of K topics. And then the way it's assigned is by using a document-specific distribution. And documents themselves belong to a distribution of topics. And to do all of this, the essential probability ingredient is a multinomial with the Dirichlet. Right? Okay, this is not too bad to understand. So a multinomial distribution, it's just, it's a generalization of Bernoulli, right? So you have K or M discrete categories, and and each category has a probability p. That's the vector. That's the probability vector. So it's like throwing throwing the die with k faces. Right? So that's the model. That's the multinomial model. So that's one realization, right? But the multinomial model has combinatorial things under the hood as well, right? Because there are many ways in which you can get. So even in binomial, right, a sequence of zeros and ones. So you can get right. So this is 1, 2, 3, 4 ones and 2 zeros, right? So I can embed the 2 zeros in many ways, right? So the binomial counts the number of ways you can get 2 zeros embedded in, right? So this is n choose x, and x is the number of ones, n is the length, right? Like that, the multinomial distribution has a more messy combinatorial structure, right? Okay, let's not go there, right? It's going to get too. But the main point I want you to understand for controlling the input to the LDA algorithm is the Dirichlet being a conjugate to multinomial. So Bayesians call this, use the word conjugate when you have some nice properties between the prior distribution and the posterior distribution. Okay, again, so many swear words, right? Okay, I think the syntax in the notebooks we can rush a little bit, but let me just give you a little bit on Bayesian prior and posterior, right? So what we are trying to basically do is, so each of these, in a lot of these generative models, we actually have a multinomial with a conjugate prior. So what is a multinomial? It's going to be a point. The parameter for the multinomial distribution is a point in the 3-simplex. Let's say we're rolling a Toblerone bar with 3 sides. Okay, so this is side 1, side 2, side 3. So for us, the 3 sides are the words. Okay, 3 different words. So we roll this. It has some central mass and it lands with some probability. So let's say P1, P2, P3. And so P1, P2, P3 is some point here, right? That's the parameter of the multinomial distribution with 3 outcomes. Now, what we really want is, so we have some observations in the classical Bayesian setting. What do we have? We have some observations. Sequence of, say, I roll this many, many times, and I look at the phase that lands on the floor. Okay, so this generalizes to any, so I can have a polygon with k sides, and I roll it, it lands, and I look at the side, that touches the floor. So, okay, that's the construction. So then I have a sequence of, so this first time 3 touch the floor, second time 2, 3 again, 3 again, 2, 3 again, and maybe just 1, 1. So this is my data usually, right? So so the likelihood function is going to be the probability of seeing, so I don't know, there's some unknown probability P1, P2, and P3. That's basically defining my my model, right? So I basically take P1 raised to the power of number of times I observed 1. I only observed one time. And then I multiply that by P2, the probability I've observed, number of times I observed 2. Okay, maybe it's a little weird. I'll put 2 twos. Okay, so 3 times I observed 2s. And then I multiply that by the probability of observing 3. That's 1, 2, 3, 4 times. Okay, so this product, okay, gives me the probability of observing this sequence, right? So if my data is actually the raw sequence, and I'm making this product assumption because I believe that this die hasn't changed, so every time I roll it, it just keeps coming out, right? So that's the independent and identical distribution assumption. So the probability of observing this sequence, conditional on this being the unknown probability, is just this, right? This is basically called the likelihood. Okay? So now, what's the basic idea in classical statistical inference using probabilistic models is just the following. I'm not really prepared for this, but you guys should know this. So you're interested in looking at the argument that maximizes the log of the likelihood function, just the likelihood function. So let's call this thing capital L of P1, P2, P3, right? Right? It's a function of, so now you think of this as a function of the unknown parameter, right? So what you're interested in the thing that maximizes the likelihood over the simplex, right? So this is what is this, capital L of P1, P2, P3. That's it, right? So what is this? This is going to be some point in the three simplex, right? So, you know, maybe if P1, P2, P3 is 1/3, it'll be right in the center here, right? And so if these sequences are like, say, 3 3s, 2 2s, 3 2s, and 3 4s, if they're equally likely, then that likelihood function will put more mass on the 1/3, 1/3, 1/3 space, right? Especially if I do this 3 million times and roughly 1 million are 1s and 2 million. So, you know, so that means that a contour sitting on the simplex, that is your likelihood function. So it's a fair-sided Toblerone bar, you know, without the grooves and stuff. So the center of mass is perfect and it'll land on all three sides equally often, right? So you will basically get a likelihood function that looks like this. And this likelihood function is itself dependent on the sample size, right? Because remember, this thing is the probability of x1, so the number of x1, so let's say n1, number of times I observed 1, number of times I observed 2, number of times I observed 3, right? Given P1, P2, P3, right? And it's just you know, P1 raised to the power of n1 and so on. So of course, if these are equally likely, then the 1/3 on the center will have more likelihood. And that will become the most likely point. So the argmax will only have one output, right? So you usually use some optimization algorithm, usually a local one to find this. You can do this using gradient descent, or if the data is too big, stochastic gradient descent, all that stuff comes in now. Now, what do the Bayesians do? So they are not just interested in the point estimate, right? So in the Bayesian paradigm, you are actually still kind of interested in a point estimate, but your point estimate itself is a distribution on this space. That's how I think of it. So basically what that means is consider all possible distributions in a class that sit on the simplex, right? So let's say, you know, you can imagine, right? There can be distributions sitting on there, continuous ones, some kind of sheet. It can be concentrated at 1/3, 1/3, 1/3, and I can keep increasing the concentration, right? By sucking all the mass from everywhere else. So that's basically like a delta function at 1/3, 1/3, 1/3. That's a possible density on the simplex. Or it could be like really hot and flat, like really balloonish, and almost every point has equal probability. That's another distribution, right? So now consider all probability distributions on the three simplex, right? Consider this. So this is our space now. I don't know, I'll call it script P, script 3. So there is this large class. Now let's say, okay, let's limit this to a subset that you know, that has some nice properties. So this is the Dirichlet distribution. So in a Dirichlet distribution, you essentially have 3 parameters that control how you have 3 parameters. Let's say alpha 1, alpha 2, and alpha 3. And so in a Dirichlet distribution, given these 3 parameters, you will get a surface here, right? And let me see. So the actual so Dirichlet distribution. So the actual thing is a generalization of beta. So it'll be x's. So here's basically what I'm talking about, right? So here you see you can have the Dirichlet distribution concentrated on one side of the simplex versus another side, and you can control how peaky it is and where it is by these 3 numbers. Okay. So let's forget the arithmetic for a minute. But if alpha 1, alpha 2, alpha 3 are say 100, 100, 100, then it's going to get super pointed at 1/3, 1/3, 1/3, right? Because how large the magnitude is controls how concentrated the Dirichlet becomes at that point. Okay. So and then you can make it, you know, concentrate here, like, you know, the first, second, or third coordinate could be close to 0, so you can have like, you know, 150, 150, and 1. So that'll put almost no prior mass on the third dimension. So this Dirichlet will focus on one corner of the simplex like this. Okay. Okay. So yeah, and then it's to really understand this. What's going on is you take each coordinate xi and raise it to the power of this alpha parameter, alpha I minus 1. And then there's it's normalizing constant with the beta functions, which are themselves products of gammas. Gets some very beautiful, very interesting maths from a few hundred years ago very quickly. But you kind of get the idea. It's just the alphas, because of this power proportionality, they control how peaky it is and where it is. And that's very important because that's what we will be controlling through our parameters in the algorithm. So, okay, finally, what Bayesians do is they'll assume there is a prior distribution on this, and they will multiply that prior specified by some alphas, with the likelihood function, right? With the likelihood function. And then they will, because the likelihood function has the data in it, right? And then, because remember, the likelihood function also sits on P1, P2, P3, right? So they can actually, likelihood function is defined on the simplex. The Dirichlet for a given alpha is defined on the simplex. You multiply the two. That's called the posterior, right? Because it comes afterwards. This is the prior. So anyway, conjugacy here basically means that for the multinomial distribution, if the prior distribution is Dirichlet, the posterior is also Dirichlet. So conjugacy just means that priors and posteriors are closed under the product operation with the likelihood. That makes it very special for Bayesian analysis and also for computational tractability, right? So I can always stay in the space of Dirichlet. So we say, for example, if I have very little information about alpha 1, alpha 2, alpha 3, then I can just put 1, 1, 1. This is the default, I think, in Spark. This basically says, or 1 over k. Let's say there are k topics, and I'm using Dirichlet to model the topics, for example. So then it may be 1 over k or whatever. So something small and equally distributed. So that will give you a very uniformish Dirichlet, okay? Because you don't know anything about your data before you see the data. And then the likelihood will will hit it, right? Likelihood reflects where the data is. Then when you take the product, you will get another Dirichlet. And I think this was maybe if I teach the course next time, I'll maybe spend a whole 45 minutes on Bayesian inference and likelihood. Then, but let's quickly go here. Okay, so here's kind of the outline. So I'm going to quickly review this data set, and in step 1, we'll download, which is downstairs, and we will start cleaning the data set, do some tokenization of text using ML pipelines. I'll remove stop words. Remember, stop words are commonly occurring words in every document. If you don't remove them, it's going to affect your analysis heavily. Okay, so it's common to remove, commonly occurring words. So you have some, unique words that are of interest. And then we will do a vector of token counts. And finally, we'll create the LDA model with online variational base, which is this method by David when he was a little bit younger. And then we will actually review the topics. If time permits, I will sort of say, what you should do to improve this. We can tune the model. We can refilter by stop words that are appropriate for your problem. There's a lot more tuning you can do. And then we'll recreate this LDA model with the other algorithm, with the expectation maximization algorithm, which is, again, a very, very powerful idea in this framework when you have graphical models with latent variables. And it also involves the likelihood function. Okay, and then we'll visualize the results quickly. So here is this 20 news groups data set that a lot of people use. Each news group is stored in a subdirectory with each article stored as a separate file. So we just keep that same file structure when we dump stuff into our distributed file store. And this is again a nice trick, especially when you're doing your project. So how did I pull all of this content out? I used pandocs. Pandoc-f HTML gives you the HTML. I mean, you can wget the file first with all the absolute links using the wget-k. And then once you have the HTML file, you can use pandoc- from HTML format to Markdown format. And then you get this Markdown file, and then you can start decorating the Markdown file. So this may be useful in your project when you want to, rip some content and embed it locally. So this is basically the Usenet articles that were from these 20 groups. So one news group was atheism, another one was computer graphics and Microsoft Windows, IBM, Mac, and so on and so forth. So as you can see, there's a lot of computer-specific news groups. There's motorcycles, baseball, hockey, electronics, religion, Christianity, politics, Middle East, and so on, right? Space, science. Okay, so approximately 4% of the articles were cross-posted, and the articles are typical postings, of people. So here is the actual papers, this stuff up here. Okay, so it's important. The mini dataset consists of 100 articles from the following 20 news groups. So it's not the full dataset. It's good enough for the community edition to get the idea. And so there should be 2,000 files in total from that. Yeah. So anyway, this is a sort of glorified version of this other simpler analysis from Databricks Notebook before. Okay, so let's just make sure we have the files. So I have my files here. And then, so I'm going to use this whole text files method, right? So this method basically will give me my file path and the content of the file as a double, right? And then I'm just mapping the second element, which is the contents of the file in this map. In this other map, I'm just converting it all to lowercase and caching it, right? So that's going to be our primary corpus. Just sucked all the contents and lowercase it. Now I just want to count. Remember, it's supposed to be 100 files, 20 topics. So there should be 2,000 documents. This will take a bit because I'm reading it and caching it, but once that's done, it should be done. So then I'm taking just the top 5 elements of the corpus here. And if you see, I'm basically getting an array, and I have a lot of details on the machines that are communicating. And then after a certain point, I have these 2 white lines, and then my actual content starts. I don't know, it's saying, however, I hate economic terrorism and political correctness worse than I hate this policy. So, so now so this is a good way to explore. So if I do corpus.takeSample false, I think it means sampling without replacement. And then I can choose how many samples I want. So this is a nice way to just randomly sample different documents and see what the content is. So that's what I did here. And so again, I did this a few times, and then I saw that there are these 2 line breaks before the actual content starts. It's not like foolproof, but this is a highly structured data, so I'm sort of hacking. So what I'm going to do is now take the mappus and I corpus, the full corpus, and then I map the split by 2 end-of-line characters. And I'm doing the backslash twice because I'm escaping the end-of-line. This is, so normally backslash n is an end-of-line character. And then I'm dropping the first part, right? Because I'm really, and then I'm making a string out of the rest of the stuff, separated by a single white space. So I should just get clean list of words now. So I'm not going to run this live because I've got to run. So we basically get a count of the 2,000 words, and then I'm again taking the top 5 and checking that it actually makes a bit more sense. Now what I want to do is feature extraction and transformation. So for this, there is each of these links. I strongly recommend you go here and look at it. there is a lot of stuff that is already pre-made for you if you want to do ETL operations on natural language processing stuff. There is feature extractors, so term frequency, inverse document frequency is a standard trick here. Word to vec, or count vectorizer is something we'll use for this one. There are other things, feature transformers, feature selectors, locality sensitive, stage operators. There's a lot of stuff. So don't roll your own, just look because it's optimized downstairs for what is better. So okay, so we're going to do text tokenization first. Oh, sorry, before that, we're going to do this. So what I'm going to do is take my corpus body and I'm going to zip with index. So I have an ID for each corpus element, right? So this is just the zip with index thing, and it'll associate an ID with my corpus. So I can sort of have this. And then next, doing text tokenization. So this, we can use a regex tokenizer. So regex is very powerful. Here we're just using it to just separate by white space, because remember we put the white space character to break the words apart. But you can do arbitrary patterns for other problems. Right. So I think for the Cornell movie lens example, I'm doing a completely different regex parsing. I highly recommend going through it. Because those guys write their files with like 4 colons or some weird strings. So we have to kind of muck around with different regex patterns. So I'm setting an input column, an output column, and now I have my tokenized data frame, which is basically, it takes my tokenizer, right? And it calls the transform method, because my tokenizer is just that transformer, right? So I've basically built my transformer, and then I'm calling the transform method on tokenizer, and I'm feeding it the corpus df. This is how you want to think about adding extra columns, basically, to your original data frame. Okay, so now the display tokenized df is here, so I can sort of display my tokens here, and you can start seeing, I did display stuff before, and someone emailed me saying, oh, please don't, whatever this user, he wanted to remain anonymous because it's some kind of politically incorrect statement and probably some big shot now. So anyway, someone emailed me saying, oh, please remove this from, because they said something a while back in the news group. So anyway, I just displayed the tokens now, but you can see the other stuff if you uncommented. So now I have my tokens nicely in an array. So next, what I want to do is remove stop words. And stop words remover is what allows you to remove stop words. So here is this, list of stop words that people use. You can go here and look at it from England somewhere, some linguistics group. So this is R, around, as, at, back, be, become, whatever. It's some 6. I don't know why 6 is a stop word, but this is the list that they have. And we basically can, so I've done it so that you don't just take the default stop words list. You can just put any set of stop words that are appropriate for your domain problem, right? Because if you do your K-mer thing, you can, I don't know, maybe you shouldn't put stop words, but you can if you want, right? Because you can have a very large collection of K-mers and use the stop words as a way to analyze different subsets, for example, because it just filters it out. All right, so here is, so this is basically the, so I'm basically loading this file and showing what it is. And then if I use the stop words remover feature in ML, I can basically create this. So this again is a transformer. It uses my customized stop words as a parameter to set stop words method, and then I have my input column and my output column, right? So I'm just calling it filtered, and my input column is the tokens I created before. So it's just my filtered df is simply this transformer called remover called with the transform method, and I'm putting the tokenized df into it. All right, so so step 5 is a vector of token counts. So here I'm simply taking my taking my vectorizer and defining this val vectorizer to be the count vectorizer. Because what does the count vectorizer do? So please follow these links to get a quick snapshot of what it does. So here's an ID, right? This is what we did with zip with index and an array of text. And I'm basically going to get my array of text converted into vectors like this, right? 3 is the total vocabulary size. A, B, C are the 3 words, and then 0, 1, 2 are essentially a representation of the characters as integers. And then this is the count. There's 1 of A, 1 of B, 1 of C. There's 2 of A, 2 of B, and 1 of C, and so on. So that we just do very quickly. Using count vectorizer, which is a transform. Okay, so yeah, so maybe we should stop and continue next time. I don't know. Yeah. So what I recommend is maybe just load this data set later on for the next class, and maybe I'll continue from here because it's kind of good to maybe do slightly slowly because there is optimization and we'll do some improvements. And then maybe for next week, I'll do recommender systems. Yeah, sorry, I didn't plan for the maths, but it's it's good that you guys know like some things at least. Okay, so
can you upload the version then with also step 1?
So step 1 is at the bottom of the document.
Oh, it's in the bottom. Okay.
Yeah, so I think step 0 probably says step 1 is in the bottom.
But I'm wondering.
It's on the, I think you had a previous 33, which also was continuous group.
Oh, wait, so
There I have it, but I didn't see the one.
I mean, yeah, I put step 1 in the bottom because you only need to load it once per shard, so that's the reason. Right? And the loading takes a while, so yeah, Databricks has its own news group stuff as well, so I haven't. Okay, so let me quickly. So, because I repeated all this yesterday, so step 1, downloading. Step 1 only needs to be done once per shard. See details at the end of the notebook for step 1. So I think it's there.
There.
Yeah. So.
But I'm wondering. So this data set news20.binary/data001.
Yes. So this is Databricks'
I
data.
have that folder. So do I need to do the steps below? Because what you end up with is a different folder than.
Yeah, so what I did was, so I didn't use this. I was using I was doing it all directly from scratch, so you could do it on something else.
Right.
So I think the analysis upstairs is on this process, so because you have to download this and load it. I mean, because I haven't tried my method on this stuff.
Okay.
Right? Because I was just paranoid. I read the original paper, downloaded the. So, and this is good because then you can do this on other things. Of course, you can do this for terabytes of data, but if you want to analyze terabytes of data, first of all, you shouldn't work on Databricks Community Edition. But if it's like a lot more data than Databricks will allow you, you can connect to S3. You have to put it in Amazon S3 and then link through it. But all the examples I'm doing, even this one and also the Cornell movie one, you can take about 10 minutes to load the data, and then you're set. But you may have to go and delete some of the other content in your Databricks Community Edition. That's the breaks. It's free. You can do this in Zeppelin, and it'll take a lot longer. But the problem with Zeppelin is I can't assume everyone has a machine that has like 6 gigs of RAM and blah, blah, blah. So that's the other problem, right? So yeah, I think, just do the C. I'm basically copying this recursively into this place, datasets mini news group, and this is the folder I'm analyzing for the rest. Yeah. Okay.